Hello and welcome to this conversation with Vubiq. My name is Frank Real. This conversation is part of Sense Affiliate report on small cell backhaul that gives an update on small cell backhaul solutions and on the evolution of the mobile operators requirement for small cell backhaul. Today we're talking to Adam Button, CEO of Vubiq, and to Mike Pettus, CTO of Vubiq. Vubiq is a new innovator in the small cell backhaul space, for particularly focusing on the 60 gigahertz space. And what I would like to do now is to turn it over to you, Adam, and start off by asking you to give us a brief introduction about your company background, and also about the small cell backhaul solution that you have.
Sure, Frank. Thank you very much. Yes, I'm Adam Button, CEO of Vubiq. Vubiq has been around for about 9 or 10 years now, exclusively focused on 60 gigahertz technology. We've developed products for the R&D market, components and development systems, and we went into video links, creating products that transmit uncompressed high-definition video wirelessly at 1.5 gigabits per second. These are for broadcast applications. That led into a nice order with the National Hockey League, the NHL, to equip every net in the NHL, all 30 teams, all 30 venues, with goal cams. These are high-definition cameras looking at the goal to adjudicate whether or not a puck crossed over the line or not, and transmitting that uncompressed video back up at 60 gigahertz to the judging booth upstairs. We've not only got theoretical and lab applications, but real-world applications of 60 gigahertz out there. We're now moving into telecom and are developing some very interesting products for small cell backhaul, utilizing both 60 gigahertz and also another unlicensed band, 5 gigahertz spectrum, for a dual cell solution.
That's a very interesting proposition here. So basically, the solution that you have, if I recall, the name of that solution was the Hall Pass. That is a dual band product that covers both the 60 gigahertz and the 5 gigahertz. Can you elaborate a little bit more on that?
Sure. Well, we are unlicensed spectrum advocates, and believe that there are a tremendous amount of advantages to using unlicensed spectrum versus paying for licensed spectrum. Both the 60 gigahertz band and the 5 gigahertz band that we're using are unlicensed, and we are incorporating both of them into a very efficiently integrated unit that will be able to transmit backhaul for telecom, both line of sight over 60 gigahertz and non-line of sight over 5 gigahertz. It can act as a failover. In other words, if you've got a line of sight connection and you're transmitting at a gigabit per second, which is what we will be doing, if something happens, if there's a huge rainstorm, if a truck passes by, if trees grow over the summer, if anything happens to block that line of sight path, our system will immediately and automatically fail over to the lower frequency 5 gigahertz transmission speed and maintain availability.
Mm-hmm. Can you comment on what sort of capacity and throughput you can handle on the 60 gigahertz and the 5 gigahertz?
Right. So at 60 gigahertz, we're at a full gigabit per second. Actually, the overall data rate is 1.25 gigabits per second in full duplex. But your payload's basically a gigabit per second, also full duplex. Then at the 5 gigahertz band, we're using a 4x4 MIMO implementation of Wi-Fi, and that will allow us to achieve 600 megabits per second. So you can have both radios going at the same time in a line of sight condition, so that the total aggregate throughput will be 1.6 gigabits per second in both directions.
So achieving 600 megabit per second for the 5 gigahertz, that's pretty tough to do. How do you achieve that?
The interesting thing about what we're doing is we're using 802.11n technology in the product, and we're using 4x4 MIMO. 600 megabits per second, of course, is the peak PHY layer bit rate that we can achieve. We have good antenna diversity in terms of the 4x4 MIMO. We have 4 antennas at each end of the link, and Adam's going to grab one of the units here that you can see. You can see the 60 gigahertz antennas here in the middle. That's a horn antenna, and then there's 4 of these 5 gigahertz antennas surrounding the 60 gigahertz antenna, and they have polarization diversity as well as spatial diversity. The other advantage of using 802.11n in a point-to-point application is that we have the ability to optimize the controls. These are not being used as access points, of course. They're being used as point-to-point bridge mode. And in so doing, we will optimize the controls for maximum throughput, maximum bandwidth, highest interference mitigation, with the knowledge that the other end of the link is us. In other words, it's a closed system. And because it's a closed system, we don't have to deal with access point issues and 802.11 access for users and those kinds of things. It's basically in a bridge mode. So we've turned on all of the high throughput, high bandwidth controls in the 802.11 MAC, such that we maximize throughput for our benefit. The good news is there's only one other location we're talking to, not many terminals.
So one thing that's associated with unlicensed band solutions is the interference issue and also the latency issue, especially when it comes, for example, to 802.11 type products. How would you address that to meet the operator requirements? And if you also can comment on what you hear from operators on the requirements with respect to latency.
Right. The expectation for millimeter wave is very low latency. Our latency, including forward error correction, is less than 20 microseconds on the 60 gigahertz link, and the 802.11n latency is less than 1 millisecond. And how we can achieve those very low latencies on 802.11n is, again, we have full control over the MAC, and we turn off a lot of the feature sets in the MAC that are generally used for access point features. So the interesting thing is that the 802.11n does have the ability to be a very low latency link if you have control of both ends, and that's what's important.
I see. So what other requirements do you see from operators, specifically on the small cell backhaul issue, and how does your product meet those requirements?
The other requirements that are becoming very, very important in carrier-grade networks are not only the physical layer, getting throughput and latency down to where they need it for LTE and LTE advanced, but also at the next layer, we'll call it layer 2 or even layer 2.5, synchronous Ethernet, 1588 P2P timing for the new LTE Advanced. In order to achieve their capacities they need, they're moving to time division duplex. And when you use time division duplex in a very dense network, you have to have very, very accurate timing and phase information to the small cells in order for them to achieve their capacity. And our radios are fully compliant with 1588v2. Our radios also supply or have GPS timing availability, and we're using a combination algorithm in our synchronization and timing such that I'll call it 1588 with GPS assist. And there's even a fallback mechanism. So some carriers are saying GPS is great. They're even using it in their small cell base stations as a method for synchronization, but they don't count on it. There may be interference. There may be a situation where they don't receive the GPS satellite signals. In that situation, we fall back to 1588 completely. In that mode, the 1588v2 and the version we're using and the implementation we're using gets us to less than 500 nanosecond phase error at the small cell base station, and that's very important for synchronization.
Okay, that's interesting. Can you maintain the same type of synchronization over the 60 gigahertz and the failover 5 gigahertz, or would the 5 gigahertz have, let's say, not as stringent tolerances?
You're right. The 5 gigahertz will probably have a wider window of synchronization error than the 60 gigahertz, simply because of the packet delay variation numbers that you incur at 5 gigahertz versus 60 gigahertz. So again, the theme behind this product is that we have multiple methods of delivery for both payload and synchronization. We have 2 bands, we have 1588 and GPS, and we feel by putting all of the tools from the toolkit into a single product is how we achieve extremely high reliability in the system. To answer your question further, we also handle full security, not only transporting, of course, transparently IPsec, which they may use in their network for security, but we are implementing MACsec, 802.1ae, MAC layer security, so that every segment, if there's repeated segments, wireless backhaul, every segment is protected and encrypted with AES 256-bit encryption, as well as being able to transport multiple streams that are isolated from each other. And what we see happening in the business model is that backhaul networks may actually transport competitive carrier streams in the future. And your equipment has to be ready to isolate and encrypt for each payload stream. And we are fully implementing MACsec at the physical layer 2 portion of the product. The other aspects that we provide are MPLS, full MPLS capability in terms of multi-protocol label switching, and full QoS capability. Customer can configure the QoS parameters, and a full rich set of OAM capability for monitoring and configuration in the network. So more than just a physical radio link, we see these units being placed out into the backhaul network as very, very capable network nodes. And what's going to happen is going to change from a point-to-point network to a partial ring, partial mesh. Adaptability is the key word here, because when they get out into the field and they realize where they have to put their small cell base stations, it's not as clean and nice as it was when installing macro cells. They just have to adapt. And the products have to be ready to work in that kind of an adapted environment.
And one reason we've got some expertise in this area is because Mike ran engineering at Metrocom for about 11 years. And Metrocom, as you may know, they put out wide area networks, wireless networks for people to access the internet before Wi-Fi even existed. So they were putting up radios on top of street lights and light poles outdoors in the city that were talking to each other in a mesh configuration, remarkably similar to the current challenge for the small cell infrastructure that we're looking at today. The major difference being that the radios today are about 1,000 times faster. So we've got a lot of experience in real-world issues, and knowing that you go out there and what's listed on a plan or a map is not the case because there's a building in the way or a billboard or a tree or something, and you've got to be able to adapt when you're out in the field.
Yeah, this is very interesting, and that's actually a whole different area in terms of the logistics, how to go and acquire these light poles and these light infrastructure assets. So what are your thoughts on this, having had this experience to go, do this in the past, and how did you design your product in order to make it even easier to deploy and save costs from a deployment and implementation perspective?
I'll make a quick comment on that before Mike answers. But one of your questions before was, what are the carriers looking for? What are we offering the carriers? And clearly, a huge of huge import to the carriers is cost. Now, not talking just capital cost of the equipment itself, we're talking total cost of ownership. And so, while our units will be very competitive on a cost basis alone, where they really shine is by minimizing the total cost of ownership because of the second major feature of this unit, which is automatic alignment and maintenance of a link. So when you set up the link, it makes it very, very easy for a low-skilled installer to hook it in, plug it in, and walk away without requiring sometimes hours that are needed for 2 installers, one on each end of the link, to get them set up, align it, optimize the link, minimize the bit error rate. That takes a lot of time. You multiply that by the hundreds of thousands of small cells that are going to be deployed over the next few years, and you see that installation cost is going to be tremendously high. And this is another feature that we think differentiates our product not only from other categories, but from other 60 gigahertz solutions. and we think will be of great benefit to the carriers.
Yeah, the auto alignment and auto stabilization feature of the Hall Pass SC is very key for carriers whose business models require a lower OPEX. In other words, if their CapEx to OPEX ratio, so to speak, is such that they want to minimize installation time and installation labor, the SC is the product to go after, which provides the auto alignment. Because the installer can put it up, he has no idea where it's pointed, he just installs it, connects it, and goes away. It's literally a 10-minute install. And what happens is the system itself automatically provides alignment of the link. And at millimeter wave, this is critical because the beam widths at those frequencies are on the order of 2 to 3 degrees. Antenna beam width, so it requires very precision alignment. Auto alignment is a great thing for reducing the OPEX. Not only that, many platforms that they're going to be mounting on, like light poles, move in the wind. I mean, it's a simple problem that the light poles are swaying in the wind, and for millimeter wave lengths, this can be a disaster because you can fall in and out of the beam as the pole is swaying. So the same mechanism that provides alignment also provides stabilization within a half a degree. And so this is a big win in terms of the ability of the carriers and the installers to, again, minimize their overhead and maintain a very reliable link. And to answer your second question here in terms of how do we provide technology, or what does our solution do to provide an answer to adaptive environments, adaptable networks. You hear a lot these days about self-organizing networks, or SON. Most of what they're talking about is at a logical layer, and of course we do that. That's just kind of given that you have to be able to adapt addresses and adapt new nodes that appear or disappear in the network. But because we have the auto alignment feature, we can physically do self-organized networking, which is something that one of the carriers said that they move things around from time to time. They want to move their positions of their base stations around, and this is a big win when you have an auto alignment feature.
Absolutely. So in terms of availability of the link and also in terms of the ongoing maintenance, that's a major cost saving. How wide can the alignment be? Can it be done vertically, horizontally, over, like how wide is it?
Okay, if you look at the Hall Pass SC product, the auto alignment range in the azimuth, which is we'll call it the pan or the azimuth range, is 360 degrees. And the auto alignment range for the elevation, which is rotating up and through, kind of on the vertical plane, is plus or minus 120 degrees or 240 degrees. So it has a lot of adaptability to point just about anywhere.
And one more point is that it can be installed inverted. Upside down. So you essentially have omnidirectional capability.
Yes. And so if you're on a tall building and you have to point down at a steep angle, you can actually invert the mounting of the unit and it'll point down that way.
All right, very good. So going back to the 60 gigahertz technology, is there anything that you're doing that would be, let's say, differentiated from the other, like in terms of the basic technology, that would be different from the other 60 gigahertz solution? And maybe here what I'm asking is just give us a little bit of a flavor of what the 60 gigahertz market and how you fit into that.
The 60 gigahertz technology we're using is now on the order of 4 years old, and we have a lot of history of developing 60 gigahertz. Our fundamental core technology is at 60 gigahertz. And the key issues with developing a reliable and manufacturable 60 gigahertz product are getting around the problems of packaging. You know about integrated circuits, and they have little leads and then put them down on the board, and it's very simple. At 5 gigahertz, it's a simple matter. You buy chips, you put them on a board, connect them to an antenna. At 60 gigahertz, you cannot use the same techniques to get the energy on and off the die or the chips because of such a high frequency. We have products, and you can see them on our website. We have our waveguide module, which is the core technology inside these radios, which is a very producible and reliable 60 gigahertz element in the radio. So that points to simply that the manufacturing cost is low for producing a millimeter wave radio. The other performance issue with these products is that some techniques at 60 gigahertz are lossy. If you don't do this right, you will lose energy or signal. We measure it in decibels, and if you have enough loss, you impact your range. In our packaging, and it's patented, the entire packaging that we use for waveguide interfaces and 60 gigahertz die interfaces are all protected under our IP, and the losses incurred in these packages is less than a decibel, and at 60 gigahertz this is very important. So this points to performance, simple performance.
And Frank, we've been shipping silicon-based 60 gigahertz products since May of 2008, just about 5 years next month. So a tremendous amount of experience, IP, whether it's actual patents or just trade secrets. We've got a tremendous amount of experience and knowledge when it comes to building high efficient, low cost 60 gigahertz products.
So another question I'd like to ask, I mean, obviously you made a conscious decision into going into unlicensed bands, 5 gigahertz and 60 gigahertz.
Yes.
How do you see that compares, let's say, to other solutions on the market? Solutions that use, for example, microwave frequencies, line of sight, point-to-point or point-to-multipoint, and also the non-line of sight solutions.
Faster, better, cheaper.
That's
okay.
Right.
Faster, better, cheaper. Now we are, as Adam said earlier, and you asked a very good question about interference. As Adam said earlier, we're unlicensed advocates. We absolutely believe that technology solutions are going to be faster and more effective than policy-driven solutions, such as licensing. That's the first thing. If you look at all of the current technologies that are going to be deployed at LTE Advanced, such as OFDM, MIMO, coding, all of these things were developed in unlicensed technologies, specifically in IEEE standards, 5 to 8 years before the cellular industry adopted them. So unlicensed technology usually gets there more quickly to market with very high technology solutions, very effective solutions, before the licensed users get to them. Number one. Number two, interference is a big question, and you asked that earlier, and I want to address that. Interference controlled by allocating fixed spectrum for users has been used traditionally in radio ever since the FCC came into existence. That's how interference has been controlled on a license basis. What's happened in the world of radio is the big word digital. As soon as digital radio occurred, and as soon as 802.11 started using digital radio techniques, OFDM, dynamic frequency selection, coding, and also MIMO, which is one of the biggest things that's hit during the last 10 years. These technologies are the best solution to interference, rather than saying, I'm going to allocate a piece of spectrum and no one else can use it but a certain entity, the licensee. The third reason, licensed spectrum, by definition, especially below 5 gigahertz, is narrowband. You might get a 10 megahertz or a 20 megahertz license. You might get it for an area, or you might get it nationwide at great expense. The 5 gigahertz unlicensed band is on the order of a few hundred megahertz wide, and it's just another 195 megahertz has just been added. The FCC made a statement at the CES show in January that now another 195 megahertz is being added. So it's not only a better technical solution, the policymakers are now realizing that unlicensed solutions are a good way to go, such that they're giving more and more spectrum to unlicensed operations. So we're big advocates of it. We think interference mitigation, first of all, at 60 gigahertz, interference mitigation is basically the phi layer. 60 gigahertz is very narrow beam width. The fall off due to oxygen absorption, which what at one time was considered a bug, is now a feature, especially in dense networks. The isolation that you can provide at 60 gigahertz, and therefore the network density that you can provide, is unbelievable compared to other spectrum. And at 5 gigahertz, the impact of using MIMO for beam steering and also beam nulling, if there's an interfering source at a given angle from the radio, MIMO has the ability to null out that source on a dynamic basis, on a packet-by-packet basis. So our answer is, let technology figure out the interference solutions rather than policy.
You also mentioned E-band and 70, 80 gigahertz solutions that are also millimeter wave. These are light license solutions, and people would say, okay, well, it's very simple. You get on the web, you fill out a small application for the link and pay a small fee, and no problem. It's a minor issue. Again, when you talk about rolling out tens of thousands, hundreds of thousands of small cells, each requiring backhaul, that becomes an entire huge process, another administrative process that's going to add cost to the carriers.
All right. So I got one final question, and that's about your roadmap and the evolution of your product. So if you can comment on this, and where do you see taking the product next?
The roadmap for this product, which is a high bandwidth backhaul product, simply points to one major area, which is bandwidth. We see the bandwidth going up over the next few years in the 60 gigahertz spectrum. At the end of our roadmap, we see 60 gigahertz carrying up to 10 gigabits per second. And we see more spectrum being added to the 5 gigahertz band, which gives us, again, more spectrum, more wideband channels. So the first parameter that you'll see change as products move along in the backhaul are bandwidth. And of course, with LTE Advanced Release 10, Release 12 coming around the corner, what's the major change that they need? More bandwidth. So that's at the top of the list. Below that, you'll see product kind of a lineup, a variation of products that fit certain needs. You know, there'll be variations of number of ports, the capability to cascade and mesh, and these types of things. So as the network complexity grows, the products have to adapt to be able to work in those highly complex networks.
All right, very good. Well, thank you very much, Mike and Adam, for a very insightful conversation. I would like also to thank the audience for listening in on this conversation. This conversation is part of Senza-Fili report on small cell backhaul that provides an overview of the small cell backhaul solutions along with in-depth conversations like this one that we just had from leading vendors who participated in the report. The report can be downloaded from the Senza-Fili website at senza-fili.com. So again, that's www.senza-fili.com. Thanks again, Adam and Mike.
Thank you for having us. We appreciate it.